what I'm talking about today is, I'm going to put this link in chat as well for people who want to visit this and peruse it. But what I'm talking about is this new ErrorTools paclet, which we recently published, paclets.com, just as a convenient way of kind of making it visible to folks internally, but to a lesser extent externally. And this, we think, is kind of it instantiates a lot of the ideas that we were trying to design, I guess, a lot of the functionality you're trying to design, but we consider it kind of an alpha release. We think it's stable enough for some level of internal usage, but we don't want to give the false impression that what we have here is a final design. And one of the things that we've been keeping in mind since the very beginning on this project is that, we know that error handling is something that has had many generations of different designs in Wolfram language. Many people have tried to kind of design, error handling facilities. And what we wanted to try to avoid with this effort was solidifying too quickly on, kind of quote unquote, the first set of ideas that came to mind. We really want to emphasize what we think is the importance of getting real world usage of this functionality and refinement of the design through that usage before we consider adding any of this to the system context and kind of stabilizing it for all coming time. So that's why we've decided to take this approach of reaching out to some internal groups, talking to people like through this venue to kind of say, hey, this thing is here before it's actually a finalized part of the system. And that's kind of one of my goals today, is to try to evangelize what we think is the utility of using this, particularly in new projects, greenfield development, where if you're looking around for how should I handle errors in this new package I'm developing, we're hoping that this can be a reasonable choice for certain kinds of projects. And the more people do that, and the more feedback we get on what seems to be working, what seems to still be perhaps some rough edges or parts of the design that aren't solving certain problems we have, we're hoping to refine this design. So what I'm talking to you today is not some finished design. It's what we have now, we think, is reasonably stable, but we're definitely looking to get feedback. So that's kind of the preamble, I guess, framing what we're trying to do here today. So let me talk a bit about what the design actually looks like. So one of the things we decided relatively early on in our effort, this wasn't obvious from the beginning, but I feel confident in our choice, is that we wanted to build this around failure objects. We didn't, one of the ideas we had at the beginning was, well, maybe we need some new representation, something that represents exceptions or something along those lines. We eventually gravitated away from that and decided, what we really want here is, when we already have this representation, failure, that's pretty general, it's pretty powerful, it does a good job of visually presenting things to the user, and we want to build on top of that. But we still need to solve some of these, problems of kind of propagation and creation of error conditions, and all the ways that those, complexify control flow in programs. But so this was really one of our core early choices. We're building this around failures. But we had a couple of other problems to solve once we decided that. One is, part of the experience we have in large software projects, again, is that actually, when you have a failure condition that occurs, you often want some kind of control flow alteration at that point. You want, when at the moment that failure is first identified in your code, it's often most convenient if that alters control flow. So another decision we made early on is that we probably wanted to base this around some kind of exception mechanism, where when a failure condition occurs, the program won't simply continue evaluating normally. It's going to break out, it's going to break off that happy path and do something different. And that was kind of inspired, obviously, as you might guess, by exception raising mechanisms that exist in all kinds of programming languages, as well as the lexical control flow capabilities of the recent confirm and close functions, which we hope to integrate this new framework with quite closely, though that hasn't quite happened yet. There are still details of that part of the design to work out. But that's the two major decisions we made. We wanted to base this around failure, and we wanted to base it around exceptions, at least as a kind of the primary manner of control flow. One other aspect of the design that I'll talk about, mostly because it's unavoidable to get out of the way at the beginning, is we have this notion of a mechanism for registering error tags for failures, which is actually what this very first function in the guide page is here, which is why I'm going to explain this a little bit. So the basic idea is, failure objects as they exist right now, they're a tag, some kind of string or symbol that imparts some identity to the failure, and then an association of additional metadata. Almost always this contains a message format string parameters to kind of visually display what the failure actually means to the user, to explain it to the user. This mechanism here is a way for you to register tags that impart certain behavior to a failure. I just want to mention that out of the way, but I'll talk a bit more about that later. The real core of this system, though, are these new raise and handle functions that are designed to be, they're directly analogous to throw and catch, but they're designed to be more ergonomic to use. They're very much like our purpose is error handling, whereas throw and catch's purpose is a bit more general. Many people use throw and catch for kind of generic control flow, but not necessarily for error condition control flow. People often use throw as a form of return because of returns weird behavior. What we really wanted was a very terse API that was said, it was definitively about error handling so that it could be short and sweet, so to speak. So that's what raise and handle are. They're essentially thin wrappers over throw and catch. So what do they actually look like in practice? Well, I'll just briefly show. So raise is essentially, you can think of it as the verb form of failure or something. It has the same argument structure as failure in that it takes a tag and an association, but it immediately throws that failure. It raises an exception where the payload is that failure object. So that means if you want, if you've tested something in your code and you say, hey, there's some condition that's not quite right, you can write this short little function name, and immediately your function's going to change control flow, throw an exception to where you're handling that. So it's quite fast to type and to read. Kind of dual with raise is this handle function, which is our analogy to catch. And handle has a couple of notable aspects of its design. One of the decisions we made early on is one of the other things we realized when kind of looking at what many projects do and kind of trying to understand the history of throw and catch. As people probably know, throw and catch have a mechanism for a kind of scoping of the throw and catch based on their own form of tags, where a particular throw can have a tag and then a particular catch can have some pattern, and catches with a pattern will only catch exceptions thrown by throws with a tag that matches that pattern. So through this mechanism, throw and catch are kind of paired together. Each catch has a corresponding, or each throw has a corresponding catch that it kind of tries to prevent catching of exceptions that maybe came from, I don't know, a callback function or something. It's just a way to make sure that the exceptions you're catching were actually thrown by the code that you wrote. Because failures already have their own tagging built in, one of the decisions we made with raise and handle was to not support any kind of annotation on the raise or handle itself about how these things get paired. Instead, we rely on the tag of the failure that's thrown. So handle very specifically does pattern matching on the tag of failures that are thrown. And that I think we think is a nice simplification, but it accomplishes much of the same purpose, I guess, that the tagging of throw and failure have. But it allows us to simplify the design a bit. The other thing that we really wanted to make sure this design had was the ability to conditionally catch failures based on, like thrown payloads based on patterns. One of the limitations of throw and catch is that they use pattern matching to decide kind of which instances of throw get caught, but they don't support a form of pattern matching where you can match on the actual value of the thing that is thrown. So handle, it's much more like, say, try catch blocks in C++ or Java or other languages that have exception mechanisms where you can provide kind of clauses that indicate which types of exceptions you want to catch. Handle affords that capability. Its rules don't match on some abstract, or like some tag associated with a particular raise. They match on the payload of the failure that's thrown. And that is a nice bit of flexibility, and that it makes it a lot easier to conditionally decide at a certain point in the program where what kinds of failures you want to catch, what kinds of failures you want to let through to be handled at a higher level, which is of use in certain types of large projects where you have a large number of different types of errors, and sometimes those errors can be handled at a lower level of context. Other times you need to wait for that error to propagate up to a higher level of context before you can handle it. So the pattern matching abilities of arrays really come in handy in that situation. So let me show some actual code examples. I'm sure that's what everyone's eager to see. So I mentioned you have to register an error tag before you do something. That's pretty simple. In the common case, it's really not doing a whole lot. I haven't actually attached much custom behavior to this error tag at the moment, but that's okay. So what does it look like when I actually throw an exception using raise? Well, like I said, the argument structure is very similar to failure, though for convenience sake, we support a syntax where formatted messages and parameters are supported in line in the function arguments. So you can easily just write a description of what went wrong at the moment you raise the exception without, say, having to wrap this in an association and say what the message parameters and message template are. But so you end up with, this is an uncaught exception, obviously, because I haven't caught anything, but we end up with a failure with the message I specified, the tag I specified, and it wasn't thrown. So raise, like I said, pairs with handle. Now, in the simple case, you can give handle, essentially a catch-all pattern. This will catch any kind of failure, no matter what it is. And it does just that. So now we get that same failure, but it's no longer uncaught. But the other usage of handle is one where you provide rules, where you can say, for a certain type of failure, this is how I want to handle it. So associate an action with the pattern, just like you would in any other kind of pattern matching context. So let's see what happens if I change this back to foo error. We can see, not typo. We can see that our error gets matched by this rule that's matching foo errors, and that we have some handler action that says, hey, this is how I want to handle this error. In our case, we just log it. But if we were to instead make this a bar error, which I actually have forgotten to register, so let me go ahead and do that. All right, now we've registered both our errors, and we go ahead and raise that bar error. We can see that this has passed through the handle. We didn't supply a handler rule for the bar errors, so it's gone to some higher level of enclosing context, which in this case doesn't exist, but it's just passed through the handle untouched. So that is the basic idea of raise and handle. Now, there's a couple of usage conventions that we anticipate being these functions have been designed to enable. So one obvious one is, we know that by convention, and it's an extremely strong convention that we're not interested in breaking, system level functions don't throw uncaught exceptions. With the exception of throw itself, it's not a good thing if a system level function has exceptions that leak out of its internals. So one of the things we've done is we've designed handle to be very ergonomic in the case that you're using it to handle exceptions at the top level in some public function. So here we've got this getTuples function just represented as a public function by the fact that it has a capitalized letter at the beginning of its name. And this happens to delegate to this little worker function we've got, which by convention, again, because it has a lowercase name, it's kind of a private or internal function, and it's allowed to throw uncaught exceptions. And by composing this operator form of handle, where the first and only argument is the rules or patterns you want to use to handle exceptions, we could very easily both read and write that this is a function that internally uses exceptions to propagate its errors, but doesn't let any of those exceptions leak out. Any failure that's raised inside the evaluation of this function gets handled, gets caught essentially and returned as a normal return value from getTuples. And I've actually got two variants of this here just to demonstrate this other function that I'll talk about in a minute. But basic idea, let's go ahead and evaluate that. And let's see what this function actually does. So this function, as a function that processes data from a file, can fail in a number of ways. Right off the bat, we first have to read the file, and that requires checking two conditions, both that the file exists and is of the type that we expect, and that it's actually a string. So here we can see the first instance of what kind of a real world program trying to check and then raise an error condition looks like. So here we check, as I mentioned, well, this has got to be a normal file type. It can't be a directory or non-existent file. If that is not the case, then we need to raise an exception saying, hey, that thing you passed in isn't what it should have been. It's not expected. It's failed this way we anticipated. And here we can really see, I think, how the syntax of raise really shines in that it's, we can provide the tag for our failure. We can provide additional metadata values for the kind of, here's some value that describes what went wrong or is associated with this condition. In this case, the path to the file that we're saying doesn't exist. And then a human readable string describing the error, what went wrong as descriptive text. And this, if it wasn't obvious, again, this throws an exception. So this statement doesn't return, it doesn't evaluate. It just causes an exception to be thrown from read file, which passes through read file, which passes through this module getTuples, and ultimately is caught way back up here by this handle. So in that way, without any kind of intermediate ceremony, having to check the return value of read file, decide whether to propagate it or not, this condition just goes straight back up to the user who called getTuples. So just to show what that looks like, we go ahead and create a little example program here. So this is a valid file. And if we go ahead and call getTuples, we can see it has the value we expect. If we call getTuples on a file that doesn't exist, we get this failure that was raised here. So with the same message, the same extra metadata attached, and obviously the tag we specified. Yeah, this is one kind of failure in our program. Let me show another thing, another case. So we've read our file, we've parsed the lines. Now we have to validate that the entries on each line do what we expect. So we have a little thing, probably a little dangerous, but we're going to use toExpression to kind of parse each line as an expression. And we're going to check that the entry that we get from that line has this form that we expect for the tuples in our data file. If it doesn't have the expected form, we're going to raise this invalid entry error, and we'll again have a nice piece of descriptive text saying, hey, entry on this particular line didn't match what we were expecting. And if we go ahead and evaluate this program again with a piece of data that's not quite in the right format, we'll see that we get this failure saying, hey, there was a problem on this particular line in the file you're processing. Didn't quite have the form you want. So that's kind of what a basic program using raise and handle looks like. I do want to show one other convenience feature we support, which is this wrap raised function. Now, wrap raised, I'm going to first show what it does, and then I'll explain how it's doing that. So I go ahead and download or evaluate this other variant of getTuples, and I will go ahead and call our, or rather, yeah, make sure we're using the invalid data, call getTuples again. And now we see we have our original failure here, this kind of lower level thing saying that a particular line had some problem. But we now also have this outer failure that provides perhaps more useful, more immediately interpretable context to the user that there was some problem with their attempt to read tuples from a particular file. And so we can really see here, this is what wrap raised has done for us. It's given us the ability to quite easily attach higher level context that's often available in functions that are literally higher level in the call stack around more detailed failures or error conditions that use details that are only known at a lower level in the call stack. So it really makes it easy to get this best of both worlds effect, where you don't have to pass down context, like what was the actual name of the file that was being processed, to maybe your helper function that's processing individual lines in that file, because you can just wrap failures at a higher level. And likewise, you don't have to pass up lower level details of, well, hey, it was this line or this pattern that didn't match, because you can be confident that that failure is still, it's not going to get swallowed or replaced by a higher level failure with less detail. It's simply going to be composed with that higher level failure by wrap raised. And so again, you really get this nice effect of being able to see first at a level of detail that's gives you enough context to understand what might be going wrong, and then drill into that with more and more levels of detail to see what actually happened, and hopefully deduce how you might fix it. And I did brush over this at the beginning because it's a little hard to describe right off the bat. But the reason we have this registration mechanisms, or one of the reasons at least we have this registration mechanism, is that we wanted the ability to have some lightweight notion of inheritance relations between failures. So as an example, and I think this is partly motivated by the databases project and other projects that have similar problems. You'll often have some kind of type that represents some lower level problem, say with a connection to a database. But you want that failure to also be considered, a more general failure that's produced by your package. And so one of the conventions we've kind of set this system up to support is that a package can do something like this, where you'll register, say, a general error tag for your package. Let's call it, say, database error. Oh, and I need to support pass a second argument. And then you would subtype that, so to speak, with more specific errors. Let's say it's a database connection error. Now, if I were to just write empty list here, there'd be no relation between this error and this error. So that would mean that if I had a handle with a pattern looking something like this that was handling database errors, this handler wouldn't recognize this failures with this tag as database errors. It would think they're some completely disconnected type of error. And the way I resolve that is by setting in here essentially a list of the so-called parent tags, or the failure tags that this particular tag inherits from. And now, if I want to raise a database connection error, I can do that by the same way, by just saying, I'm going to some problem with the database connection, and we'll just check. Okay, that raises the failure as we expect. Now the formatting is a bit broken at the moment because we don't yet support this, but you can see that the tag for this failure is no longer, it's not a scalar value, it's actually a set of tags. This failure is an instance of multiple different types of errors that again have this kind of inheritance or hierarchical relationship. So if I want to handle this now as I described, let me say, let's try, we'll just say this is, I don't know, our connect function. We'll go ahead and define that. And we'll say that after calling connect, we really want to handle failures that are database errors. Now, if I were to just write something like this, which is what I wrote in this case here, where I literally wrote out a failure, this wouldn't work. At least the code would be a bit cumbersome to write if I had to write, I don't know, something like, list where member queue, database connection error. That would be a mess. So instead of writing that, we also support a failure pattern object, which essentially does this abstraction over whether failures have a tag or list of tags. Actually, I wanted to make this database error to illustrate the generality of this. And now if I say problem with the database occurred, and print that error, we can see that even though the original failure is a database connection error, it's considered to be a failure in the database error hierarchy and gets handled by this handler rule. Yeah, so that's the idea of failure tags. They're kind of a lightweight way of giving some hierarchy to the identity of failures. So you can do exactly this kind of thing. The other thing that, and I'll connect this to the idea I mentioned earlier about why we don't support tags on raise and handle themselves, is because this ability to kind of have a general tag means that what we kind of anticipate will happen in practice is what I've done in a number of projects that I've converted to use this framework, that you'll kind of define an error tag for your package. So you might have, say, an interpreter error, or in this case, a database error, or I have a paclet tools error. And I can be confident that no other code should be raising failures using my error tag. It's a symbol that exists in my context. It's part of the implementation of my package. And that gives me great confidence that I'm only going to handle errors in my package that were raised by my package. I'm not going to accidentally be handling exceptions thrown as control flow, or exceptions thrown from, say, callback functions that are passed into one of my functions. So yeah, that's another benefit of the tagging system, is that it gives that kind of scoping for quotes unquote for free. So this section of the guide page is functions that are purely and completely intentionally designed to raise errors that users should never see, but that are very useful during the development process, where code is being changed, refactored, renamed, etc. And in a highly dynamic language like ours, it's often hard. Like refactoring is often difficult because things that conceptually to the mind of the human are an error are not an error as far as the language is concerned. If a function is called with arguments that don't match any of its down values, that's not an error, it's just unevaluated. And so there's kind of a lot of overhead in trying to do things more strictly, more carefully. And these utilities try to reduce that overhead to the greatest extent possible. So a simple one is raise assert, which possibly this isn't really necessary, though I think the utility of this is that it's an assert that's kind of always on in some sense. It's if there's a part of your logic that you expect to be true, but you really need to never not be true, you don't want it to be something that's in the hands of the end user to do something like off of assert. You really need this to be conditioned to be checked no matter what, even if you don't expect it to occur. Raise assert is intended for that use case. It changes control flow, raises an exception if the condition is not true. This is kind of standard. These other two I think are a bit more interesting in terms of our ecosystem. So confirm replace is just replace, but it raises an exception if none of the values, none of the rules match. So it's kind of a way of approximating exhaustive pattern matching, which you can get in certain statically typed languages, where you can just check at compile time every possible value has some pattern that matches it. This is meant for that use case, and it's a code readability thing. You shouldn't use confirm replace to raise errors that you expect the user to see, but it's a very strong indicator to readers of the code and to you when you're changing your project and maybe you accidentally break something. You can be confident that something isn't silently not doing what you expect. That replace that you expected, it's got to be like an integer or a list of integers, but actually it was given a list of strings. You can handle the two cases you care about and then be confident that if somehow a case you didn't anticipate gets through, you're going to get a very clear error message saying what went wrong. That's what confirm replace is used for. And then set fall through error it's set in that it mutates a symbol, and what it does is add essentially a triple underscore down value to a symbol that raises an exception. You've passed arguments to this function that you shouldn't have passed to it. And this is particularly useful in quote unquote internal functions to a package. They're not public. You don't expect end users to call them willy-nilly with random arguments. You expect that you're the one calling them, and you hope that you're only calling them with arguments that are valid. So again, not useful for raising exceptions that end users will see, but very useful during the development process, where you just want your program to fail fast and clearly when something that you didn't expect happened. And as well, if God forbid a user ends up seeing that, at least it makes for a very clear bug report that function XYZ was called with these particular arguments that didn't match. Let me show an example of this, just so it's here, just as you can see. Here, if we call get tuples with something that is not a file, we get a message saying this symbol get tuples was called with arguments that didn't match, and we can actually go and inspect what that argument sequence was. And again, users shouldn't see this, but if somehow they do, it's a very clear bug report. There's some internal function that wasn't called with the right arguments, and it's hopefully now that much easier to debug. You could have, the existing behavior where essentially it raises a logic error. You could have it return a failure instead, and optionally provide the kind of format arguments and message for that. You could have it perhaps, just this is a more convenient way of a short form for saying that this function should issue a message and return unevaluated if none of its arguments matched, that kind of thing. So, like I said, this design is very in flux. But this is a really crucial point, because I mentioned that we are here trying to encourage people to use this functionality. We have defined, and the general idea is that the error handling package right now, or this ErrorTools package, which I guess I actually haven't shown a need statement yet, but the context is Wolfram backtick ErrorTools. The way this package works is that it's actually formed from versioned subcontexts that are part of the package. And if you want to use it, depending on what kind of API stability guarantees you want, you can use it in one of two ways. The first is by doing Wolfram ErrorTools. And if you do this, you get, I go ahead and list the symbols that I've gotten. Just go ahead and print these out. I get a bunch of symbols, and these symbols come from the V1 version of the context. So that's what it means. Like if you're loading this context, you're getting whatever the within the current release cycle stable version is. So what we mean by that is that we have this V1 context that defines all the functions I've just shown you, and it has a bunch of tests to kind of make sure that we don't accidentally break the behavior that we've committed to. And we're guaranteeing that if you include this V1 context, you are not going to get breakage. Like we will not break your behavior, period, if you're including a particular version context like V1. You're good for all coming time. I mean, maybe in like a few years, we'll start to deprecate these things and encourage people to migrate away from them. But the short of it is you can be confident nothing's going to break. So that's what happens if you use the V1 context. If you use this context, then we're guaranteeing that anything that goes into this context during a particular Wolfram language release cycle will not break at least until the next Wolfram language release cycle. So this is for people who want maximum stability. This is for people who want to know that they're on not quite the bleeding edge, but kind of the latest quote unquote long-term support version, where long-term support means one of our release cycles. Now, in both cases, when we introduce a new version subcontext that people might be interested in, or when we change the behavior of including this default context, we're going to send out, certainly a loud warning saying what's changing, and ideally as well, a sort of migration guide. Like here is precisely what's changing. Here are, say, the forms you need to grep for in your code to update if there's anything that's changed in a backwards incompatible way. And yeah, that's the idea. So yeah, if you want to use this, including one of these contexts in your package is the way to go. There are a couple of other things that we think will probably eventually incorporate into this tag mechanism. One is a notion of like a validator function. So for example, I mentioned earlier the case of a file error. We might support a syntax like this, or let's say, we register the centralized file error, it has no tags, and then there's a validator function, which essentially just says, I don't know, something like this. And the idea is that this would be essentially a way of enforcing that every instance of the file error that gets raised has to match this validator function. Just as a kind of way of trying to enforce consistency on the error hierarchies that we're building in the system. And that this is important for making sure that somebody who wants to handle a file error can be confident that in their handler, it's going to have a file path key that they can look up and process. And one other thing is, people may have noticed, and this is one of the kind of more controversial aspects of this design, I would say, is that right now we have our error handling is very based around message names. Some descriptive text that is assigned to a message name value that is remote to where that message name actually ends up getting used. So that's clearly very different than what we're kind of suggesting as a convention here, where the descriptive text is written in your source code in essentially English. And this has a number of problems, the most obvious of which is that it makes localization harder. Like, one of the reasons we have this message name system is to support this ability to do automatic localization based on your current language value. And the trade-off here, like one of the things we're hoping to be able to do here is that we want to make it easier for people to write errors, right? Like right now, and this may just be me, but I imagine that other people have this same problem. The need to declare your messages in some centralized location often gets in the way of when you're writing a piece of code. Oftentimes there's just as many error conditions as there are statements trying to handle errors as there are statements trying to do kind of the quote unquote happy path logic of your function. And what that means at scale is that people are discouraged, they're nudged away from writing descriptive error messages because it's pretty cumbersome to go back and forth between the file where you're actually checking for the condition of the error and raising it, or initiating the message, and your list of messages that you typically keep in a different file or at the top of a file where you have to scroll between it. And so what that means too is that people tend to, there's this pressure over time to write more generic, reusable error messages, but that are less helpful, less descriptive than they might be. One of the things we hope to be able to do with this system is encourage people to write messages kind of in plain text in here, but continue to do localization through essentially, a localization function that you can also register associated with an error tag, or maybe implemented more generally, so that you write in English here, and then in your localization code, there's a lookup on not some abstract key like a 6-character message name, but the actual English description of the error. And we would plan to support that with tooling so that we could have lint runs, linters run on a code base and check that every message that, every textual message that appears as an argument to raise has an entry in the localization database for all the languages we care about. So it'd be a slightly different model for how we ensure localization gets done, but hopefully, be advantageous for the goal of making errors easier to write without making localization less consistent.